Greetings, curious humans! Welcome back to another exciting episode of our cosmic journey. Today, we embark on a captivating exploration of the red planet itself, Mars. Mars, the fourth planet from the Sun, has captivated the human imagination for centuries. In this video, we'll dive deep into the wonders of Mars, uncovering its geological history, investigating the potential for life, and examining the ambitious plans to send humans to this enigmatic world. Over the years, we've sent a fleet of robotic explorers to unveil the secrets hidden beneath the Martian surface. Join us as we delve into the astonishing discoveries made by these scientific trailblazers. Mars boasts stunning features that are reminiscent of science fiction movies. Prepare to be awestruck as we take a virtual tour across this alien world. One of the most intriguing questions surrounding Mars is whether it could harbor life. Could Mars be a place where life once thrived or even exists today? Join us on this quest for answers as we explore the tantalizing clues hidden within Mars' red sands. The dream of humans setting foot on Mars has inspired generations. We'll uncover the audacious plans of space agencies and private companies alike, who envision sending humans on the epic journey to the red planet. So, fasten your seatbelts, fellow space travelers, as we embark on a thrilling adventure to the mysterious and alluring world of Mars. Get ready to explore its wonders, unravel its mysteries, and push the boundaries of human exploration. Don't forget to hit that subscribe button and join our community of curious minds as we unlock the secrets of the cosmos together. Until then, let's set our sights on the red planet. Mars is the fourth planet from the Sun and is known as the red planet due to its reddish surface color caused by iron oxide dust. It has a radius of 3,389.5 kilometers and a surface gravity of 38% that of Earth. Mars has a thin atmosphere primarily composed of carbon dioxide and two small moons, Phobos and Deimos. The planet is geologically active, experiencing dust devils and Mars quakes. Notable features include Olympus Mons, a large shield volcano, and Valles Marineris, one of the largest canyons in the solar system. Mars has a similar celestial motion to Earth, resulting in seasonal changes in temperature variations from -110 degrees Celsius to 35 degrees Celsius on the surface. A Martian day, Sol, lasts 24.5 hours, and a Martian year is 1.88 Earth years. Mars formed approximately 4.5 billion years ago and underwent periods of meteor impacts, valley formation, erosion, and potentially the presence of water oceans during its early history. Widespread volcanic activity and flooding occurred during the Hesperian period, followed by geological processes influenced by wind during the Amazonian period. The existence of life on Mars remains uncertain. Mars has been known since ancient times and is named after the Roman god of war. Its distinct features and brightness in the sky have made it a popular subject for telescopic observation. In recent decades, Mars has been extensively explored by unmanned spacecraft and rovers. The first flyby, orbiter, and landing on Mars were achieved in the 1960s and 1970s. Currently, there are multiple active probes orbiting Mars or operating on its surface. Mars is a significant target for future human missions beyond Earth. Scientists have proposed that Mars formed through a process of runaway accretion during the early solar system. The planet exhibits unique chemical features due to its position and the energetic solar wind from the young Sun, which pushed elements with low boiling points, such as chlorine, phosphorus, and sulfur, outward, making them more abundant on Mars than on Earth. After planet formation, Mars experienced a period called the Late Heavy Bombardment, resulting in extensive impact cratering on about 60% of its surface. Immense impact basins, including the massive Borealis Basin in the Northern Hemisphere, were formed during this time, possibly caused by a collision with a Pluto-sized body around 4 billion years ago. The geological history of Mars is divided into three primary periods: the Noachian period, which occurred 4.5 to 3.5 billion years ago and is characterized by large impact craters and possible water flooding; the Hesperian period, lasting from 3.5 to 2.9 billion years ago, marked by extensive lava plains; and the Amazonian period, which began around 3.3 to 2.9 billion years ago and continues to the present, featuring diverse surface features and the formation of Olympus Mons, the largest volcano on Mars. Geological activity is still ongoing on Mars, with recent occurrences including sheet-like lava flows and water flows in grabens. The planet has a diameter approximately half that of Earth, with a surface area slightly smaller than Earth's total dry land. Mars has a lower density and surface gravity, about 38% of Earth's, and its reddish appearance is due to the presence of iron oxide, or rust. The internal structure of Mars consists of a dense metallic core primarily composed of iron, nickel, and sulfur, surrounded by a silicate mantle. The planet's crust is composed of elements such as iron, magnesium, aluminium, calcium, and potassium, with an average thickness of about 50 kilometers. Mars is seismically active, as evidenced by over 450 recorded Marsquakes and related events detected by the InSight lander. Recent analysis suggests that Mars has a liquid core, with a radius of about 1830 kilometers and a temperature around 1900 to 2000 Kelvin. The Martian core is unusually large, accounting for more than half the radius of the planet and about half the size of Earth's core. It is believed that the core may contain lighter elements like oxygen and hydrogen, in addition to the iron-nickel alloy and approximately 15% sulfur. The mantle of Mars appears to be solid down to a depth of about 500 kilometers, beyond which a partially melted asthenosphere and a transition zone extend toward the core. Mars is a terrestrial planet with a surface primarily composed of minerals containing silicon, oxygen, metals, and other rock-forming elements. The predominant rock type on Mars is tholeiitic basalt, although some areas have higher silica content resembling andesitic rocks or silica glass. Regions with low reflectivity suggest the presence of plagioclase feldspar, while northern low albedo regions contain elevated levels of sheet silicates and high silicon glass. High calcium pyroxenes and localized concentrations of hematite and olivine have also been identified. The Martian surface is covered by fine iron, oxide dust. Although Mars lacks a structured global magnetic field, observations indicate magnetization in certain areas, suggesting past reversals of its dipole field. This paleomagnetism resembles the alternating bands found on Earth's ocean floors and has been proposed as evidence for ancient plate tectonic activity on Mars. The planet's crust carries magnetic signatures, but its magnetic field has diminished over time. Analysis of Martian soil by the Phoenix lander revealed a slightly alkaline composition containing elements such as magnesium, sodium, potassium, and chlorine, similar to nutrient-rich soils on Earth. The soil's pH is basic, 7.7, and it contains 0.6% perchlorate salt, which is toxic to humans. Streaks are commonly observed on Mars, appearing on steep slopes of craters, troughs, and valleys. These streaks start dark and lighten over time. They often follow the edges of boulders and obstacles and are believed to result from avalanches of bright dust or the activity of dust devils. Various theories, including the involvement of water or organic growth, have been proposed to explain their formation. Radiation levels on the Martian surface average around 0.64 millisieverts per day, lower than the radiation experienced during the journey to and from Mars. For comparison, radiation levels in low Earth orbit, where space stations orbit, are approximately 0.5 millisieverts per day. Hellas Planitia has the lowest surface radiation, with lava tubes southwest of Hadriacus Mons potentially reaching levels as low as 0.064 millisieverts per day. Johann Heinrich Madler and Wilhelm Beer were the first areographers, known for their mapping of the Moon. They also made significant contributions to the study of Mars. They established that most of Mars's surface features were permanent and accurately determined its rotation period. In 1840, Madler created the first map of Mars based on 10 years of observations. Features on Mars are named using various sources. Albedo features are named after classical mythology, while craters larger than approximately 50 kilometers are named after deceased scientists, writers, and contributors to Mars research. Smaller craters are named after towns and villages with populations under 100,000, and valleys are named after the words for Mars or star in different languages. The topography of Mars shows a dichotomy between the northern plains, flattened by lava flows, and the southern highlands, marked by ancient impact craters. The northern hemisphere may have experienced a massive impact event billions of years ago, creating a crater larger than any on Earth. Mars has over 43,000 identified impact craters, with Hellas being the largest exposed crater and visible from Earth. Other notable impact features include Argyre and Isidis. Mars also exhibits the impressive Valles Marineris, a canyon system stretching 4,000 kilometers, 2,500 miles, in length and up to 7 kilometers, 4.3 miles, in depth. Valles Marineris likely formed due to crustal collapse caused by the swelling of the Tharsis region. It has been proposed that Valles Marineris is not just a graben but a plate boundary, potentially indicating a two tectonic plate arrangement on Mars. Additionally, cave entrances have been detected on the flanks of the volcano Arsia Mons. These caves, known as the Seven Sisters, exhibit dimensions ranging from 100 to 252 meters, 328 to 827 feet, in width and estimated depths of 73 to 96 meters, 240 to 315 feet. These caves may extend deeper and wider below the surface and offer potential protection from harsh environmental conditions. Overall, Madler and Beer made significant contributions to Mars research, particularly in mapping its surface features and advancing our understanding of the planet's geology. Mars lost its magnetosphere about 4 billion years ago, which exposed its atmosphere to direct interaction with the solar wind. This interaction has led to the loss of atmospheric particles, causing a decrease in atmospheric density. The Mars Global Surveyor and Mars Express missions have observed ionized atmospheric particles trailing off into space behind Mars, and the MAVEN orbiter is studying this atmospheric loss in detail. The current atmospheric pressure on the Martian surface ranges from a low of 30 pascals to over 1,155 pascals, with an average pressure of 600 pascals. Compared to Earth, the Martian atmosphere is much thinner, with a mean surface pressure only 0.6% of Earth's. The composition of the Martian atmosphere is primarily carbon dioxide, 96%, along with argon, 1.93%, nitrogen, 1.89%, and traces of oxygen and water. The atmosphere is dusty, with particles about 1.5 m in diameter, giving the Martian sky a tawny color when viewed from the surface. The presence of iron oxide particles can also give the sky a pink hue. Methane is found in the Martian atmosphere, with concentrations fluctuating seasonally. The source of methane is still under investigation and could be either non-biological processes or potentially Martian life. Mars lacks a global magnetic field, but auroras have been detected on the planet. The distribution and types of auroras on Mars differ from Earth due to the absence of a global magnetic field. Martian auroras can extend beyond the polar regions and encompass the entire planet. Radiation levels on the Martian surface can increase during solar storms, resulting in brighter auroras. Mars experiences seasons similar to Earth due to its axial tilt. However, the Martian year is about 2 Earth years long, resulting in longer seasons. Surface temperatures on Mars range from lows of about -110 degrees Celsius to highs of up to 35 degrees Celsius in equatorial summer. The thin atmosphere, low atmospheric pressure, and low thermal inertia of Martian soil contribute to the wide temperature range. Mars receives only about 43% of the sunlight that Earth does due to its greater distance from the Sun. Mars is known for its large dust storms, which can reach speeds of over 160 kilometers per hour. These storms can vary in size, from local storms to global events that envelop the entire planet. They are more frequent and intense when Mars is closer to the Sun and have been observed to increase the global temperature of the planet. Mars has significant evidence of water in various forms. While liquid water cannot exist on the surface due to the low atmospheric pressure, water ice is present at both polar ice caps and trapped within the Martian cryosphere. Radar data from Mars Express and the Mars Reconnaissance Orbiter have revealed large quantities of ice at the poles and middle latitudes. The South Polar ice cap alone contains enough water ice to cover the entire planet's surface with a depth of 11 meters if melted. Additionally, the Phoenix lander directly sampled water ice in shallow Martian soil in 2008. There are numerous landforms on Mars that strongly suggest the past existence of liquid water on its surface. Outflow channels, such as Maadam Vallis, indicate the catastrophic release of water from subsurface aquifers. Dendritic networks of valleys, found in older areas of the Martian surface, imply the presence of runoff resulting from precipitation in Mars' early history. Crater and canyon walls display features similar to terrestrial gullies, which are believed to result from the action of liquid water, possibly from melting ice. The polar ice caps on Mars consist primarily of water ice, with seasonal variations of frost and sublimation of carbon dioxide. The South Polar Cap has a permanent dry ice cover about 8 meters thick, while the North Polar Cap contains about 1.6 million cubic kilometers of ice. The caps exhibit spiral troughs formed by katabatic winds. Observations from various Mars missions have provided evidence of hydrated minerals, such as jarosite, goethite, and gypsum, which typically form in the presence of water. The Curiosity rover detected hydrated calcium sulfate in several rock samples, and the Mars Reconnaissance Orbiter found evidence of hydrated brine flows and recurring slope lineae, dark streaks, on slopes. However, the role of liquid water on the Martian surface remains uncertain, and further research is needed to confirm its presence and extent. There are suggestions that Mars might have had a large ocean in its northern plains, but this theory is still controversial. Scientists have also detected a significant amount of underground ice in the Utopia Planitia region, and the Valles Marineris Canyon system shows indications of subsurface ice. In summary, Mars exhibits abundant evidence of water ice in its polar caps and subsurface, as well as landforms that suggest the past presence of liquid water on its surface. While liquid water cannot exist under current conditions, the history of water on Mars remains a subject of ongoing research and exploration. Mars has an average distance from the Sun of about 230 million kilometers and an orbital period of 687 Earth days. A Martian day, or sol, is slightly longer than an Earth day, lasting 24 hours, 39 minutes, and 35.244 seconds. A Martian year is approximately 1.9 Earth years, or 1 year, 320 days, and 18.2 hours. The axial tilt of Mars is 25.19 degrees relative to its orbital plane, similar to Earth's tilt. This tilt gives Mars seasons that are nearly twice as long as Earth's due to its longer orbital period. In the present epoch, the North Pole of Mars is oriented close to the star Deneb. Mars has a relatively high orbital eccentricity of about 0.09, with only Mercury having a larger eccentricity among the planets in the solar system. However, in the past, Mars had a more circular orbit. Approximately 1.35 million Earth years ago, Mars had an eccentricity of around 0.002, significantly lower than Earth's current eccentricity. Mars's cycle of eccentricity spans 96,000 Earth years compared to Earth's 100,000-year cycle. Mars and Earth have a synodic period of 779.94 days, during which Mars approaches Earth. Earth orbits the Sun closest to Mars's orbit, making their closest approaches, known as inferior conjunctions, the second closest for Earth, after those with Venus, and the closest for Mars to any other planet. The gravitational potential difference between Mars and Earth is the second lowest for Earth and the lowest for Mars compared to other planets. Mars has two small natural moons, Phobos and Deimos, which orbit close to the planet. Their origin is uncertain, but a popular theory suggests they were asteroids captured into Martian orbit. Phobos and Deimos were discovered in 1877 by Asaph Hall and were named after characters from Greek mythology associated with war and fear. Phobos rises and sets much faster than Earth's moon, while Deimos rises slowly due to its orbit being just outside synchronous orbit. Phobos's orbit is gradually decaying, and in millions of years, it may either crash into Mars or break up into a ring. The origin of Phobos and Deimos is not well understood. They have low albedo and composition resembling asteroids, which supports the capture theory. However, their circular orbits near the equator are unusual for captured objects. Alternative possibilities include early accretion in Mars's history or involvement of a third body or impact disruption. Recent evidence suggests a porous interior for Phobos and a composition resembling Mars itself, pointing to an origin from material ejected by an impact on Mars that reaccreted in Martian orbit. There may be undiscovered moons smaller than 50 to 100 meters in diameter around Mars, and a dust ring is predicted to exist between Phobos and Deimos. Another possibility is that Phobos and Deimos are remnants of a larger moon that formed from debris of a large impact on Mars and were later destroyed by a more recent impact. Throughout history, Mars has captured the interest and curiosity of various civilizations. The ancient Sumerians referred to Mars as Nergal, a minor deity initially, but later gaining significance with his main cult center in the city of Nineveh. Mesopotamian texts described Mars as the star of judgment of the fate of the dead. Ancient Egyptian astronomers also observed Mars as a wandering object in the night sky and were aware of its retrograde motion by 1534 BCE. In the Neo-Babylonian Empire, Babylonian astronomers made regular records of the positions and behavior of the planets, including Mars. They discovered that Mars completed 37 synodic periods, or 42 circuits of the zodiac, every 79 years. Greek astronomers knew Mars as Pi Upsilon Rho Epsilon Iota, while the Romans named it Mars after their god of war. During the 4th century BCE, Aristotle observed Mars disappearing behind the moon during an occultation, indicating its greater distance. Ptolemy, a Greek astronomer living in Alexandria, addressed the orbital motion of Mars in his work, the Almagest, which became a fundamental treatise on Western astronomy for centuries. Ancient Chinese astronomers were also aware of Mars by at least the 4th century BCE, referring to it as the fire star in their traditional whooshing system. In the 17th century, Tycho Brahe measured the diurnal parallax of Mars, which Johannes Kepler used to calculate the planet's relative distance and determine its elliptical orbit. Italian astronomer Galileo Galilei observed Mars through a telescope in 1610, and Dutch astronomer Christiaan Huygens created the first map of Mars displaying terrain features. In 1877, Giovanni Schiaparelli produced the first detailed map of Mars, identifying features he called canali, which were later determined to be an optical illusion. The observations of Mars and the belief in seasonal changes and canals fueled speculation about the existence of life on Mars. However, as better telescopes were used, fewer canali were observed, and the hypothesis of a dead planet gained acceptance after the Viking life detection experiments in the 1970s. Since then, numerous spacecraft from various countries, including the Soviet Union, the United States, Europe, India, the United Arab Emirates, and China, have been sent to Mars to study its surface, climate, and geology. These missions have provided detailed maps and data, challenging previous conceptions and expanding our understanding of the planet. Currently, there are 13 functioning spacecraft on Mars, including orbiters and landers. Planned future missions include the Rosalind Franklin rover mission, aimed at searching for evidence of past life, and a joint NASA-ESA mission to return samples from Mars. These missions continue to advance our knowledge of the red planet. During the late 19th century, there was a widespread belief in the astronomical community that Mars had conditions suitable for supporting life, including the presence of oxygen and water. However, observations made in 1894 and 1909 using improved instruments failed to detect significant amounts of water vapor or oxygen in the Martian atmosphere, contradicting previous measurements. It wasn't until 1925 that these findings were confirmed by W. S. Adams, debunking the myth of Mars' Earth-like habitability. The current understanding of planetary habitability favors planets with liquid water on their surface, typically within the habitable zone of a star. Mars occasionally dips into this zone during perihelion, but its thin atmosphere and low pressure prevent the existence of liquid water for extended periods. While evidence suggests that liquid water may have flowed on Mars in the past, recent discoveries indicate that any water on the planet's surface may have been too salty and acidic to support regular terrestrial life. Mars presents several challenges for sustaining organic life, including limited heat transfer across its surface, lack of a protective magnetosphere, and insufficient atmospheric pressure to retain water in liquid form. The planet is considered geologically inactive, which has halted the recycling of chemicals and minerals between its surface and interior. Various missions, including the Viking landers, Spirit and Opportunity rovers, Phoenix lander, and Curiosity rover, have conducted in situ investigations on Mars. While the planet may have been more habitable in the past, the existence of life on Mars remains unknown. The Viking missions in the 1970s produced controversial results regarding the detection of microorganisms in Martian soil. Positive results, such as a temporary increase in CO2 production when exposed to water and nutrients, were later disputed, leading to an ongoing debate. Recent tests by the